Before getting started, I'd like to take this opportunity to express my thanks to not only open source contributors like you guys, but also a lot of developers inside Samsung Electronics for this work. More than 30 developers were involved in this project, so I'd like to appreciate them for their passion and effort to this work. Okay, let's get started. Presentation outline is like this. First, I'm going to talk about why virtualization is so important in automotive industry. Then we're going to take a look at the key requirements for automotive virtualization. Then I will explain how we designed and implemented our automotive virtualization solution. After that, I will give you some evaluation results of our work. Then let me finish this presentation with a short video clip. Okay, let me begin by talking about why virtualization is so important in automotive industry. I think you guys already understand the reason, but I think that there are three reasons like this. First of all, is firmware update for automotive system. Firmware update is one of the major concerns that automotive OEMs have. So they have been looking for the kind of easy way for firmware update. So with virtualization, they can maintain kind of separate partitions like critical partitions, non-critical partitions, or something else. So virtualization paved the way for the firmware of one partition to be updated very easily without affecting the other partition. That is the first reason. And second reason is enhancing the security. And today, security becomes more important than before because almost every car is connected to the internet, and a lot of attackers are turning attention to vehicles these days. So virtualization provides kind of strong security because a virtual machine can encapsulate a subsystem. As a result, we can provide strong isolation between virtual machines. So we can provide kind of a secure computing environment for next generation automotive system with virtualization. And last thing is cost and complexity reduction. According to research firms' information, today's ordinary car has about 70 ECUs on average, and for the premium model, more than 100 ECUs. So the more the number of ECUs and the greater cost and complexity the automotive system has. So virtualization is useful for the lower the cost and complexity of the automotive system based on its consolidation feature. Now let's take a look at the key requirements. Before designing our automotive virtualization architecture, we identified the key requirements for the automotive virtualization through the discussion with people from automotive industry, like OEMs and Tier 1 companies. So the first requirement we identified was fast startup. It's hypervisor fast startup. Many people want to have a kind of prompt interaction with their cars, especially when they fire up the car. So if the guest operating system on top of our hypervisor is kind of very lightweight or real-time operating system requiring short green time, then this hypervisor fast startup feature is very critical, very important requirement. So this is the first requirement. The second requirement is fault recovery for reliable in-vehicle services. Different from smartphones, automotive system is more like mission critical system. So it is also important to provide a kind of instant fault recovery feature for consistent in-vehicle services. Last thing is high performance graphics support for guest operating system. Today's automotive system is trending toward adopting kind of full-fledged operating system like Linux or Android, because many people want to have the same user experiences like they are doing with their smartphones now. So it is also important to kind of full feature of graphics, like latest graphics APIs and high throughput in case of the intensive graphics workload inside the desktop operating system. This is very important requirement from automotive industry. So this is our overall architecture. In order to meet these three important requirements, we designed our kind of reference architecture like this. We implemented kind of fast startup feature inside the hypervisor together with fault recovery feature. And on top of our hypervisor, we have two operating systems like this, domain 0 and domain new. In our architecture, domain 0 is a control operating system. At the same time, it is cluster operating system, having dashboard UI. And the other one, domain new, is a IDI operating system, having IDI platform like Genedy or Android Auto or something. So in our architecture, in domain, we have kind of virtualization backend module, like virtual I/O backend device drivers and virtual backend module together with native device drivers and Gen tools and fault recovery module. In domain, we have virtualization front-end module like virtual I/O front-end device drivers and virtual graphics front-end module together with fault recovery module and pass-through I/O device driver for accessing the device exclusively from the view. Let me explain these things one by one more detail. First, I'm gonna explain how we optimize our hypervisor for the fast startup. First, we reduce the memory initialization time. For Gen startup, Gen heap initialization should be done based on the function calling like free heap pages. This function invocation is per page basis. That means we have to invoke this function every 4 kilobyte page. Also, we have kind of, in this function includes kind of, heavy operation like spin log and, kind of merge operation based on body allocator. So the cost of, Gen initialization is very high because we have to invoke this function so many times, like in proportion to the, number of total page sizes the automotive system has. So as a result, it causes a lot of overhead at the boot time. In order to reduce this kind of overhead, we implemented a new function like fast boot insert page for Gen initialization. Within this function, we insert kind of order of 2 size, very large contiguous page chunk instead of full page insertion. Also, we remove spin log from our code because we just use single core, so there's no race conditions for the memory initialization. Finally, we skip scrolling pages because we don't use any dynamic memory allocation mechanism to get operating system. Also, we don't use kind of technology like ballooning. Instead we use just static memory allocation to get operating system. So let me explain more detail. Actually, we have information like this. We have the site, the address and the size of virtual machine. Each virtual machine specify the device tree. With this information, we could assign the memory directly to virtual machine, not using Gen heap. So that means we could exclude this memory area from generic insertion operation. So as you can see with this figure, there are two steps for the original generic insertion and the memory allocation to guest operating system. The gray area is generic insertion operation. First step is generic insertion. After that, we can allocate memory to the gen heap. But the added rectangular area is kind of double assignment. That could be an overhead. So we remove this overhead. So we just directly assign memory to virtual machine. By doing so, we could improve the performance great deal. Second technique is done on DT manipulation. In order to start up, we need kind of special node information like memory information. Basically, we have to scan the entire device to get this kind of information. But the thing is that if the device tree is large, then it takes a lot of time because we have to traverse all the device tree. So we made a kind of special group, including kind of must-have node for the booting, like chosen node and memory node. And we put this special node at the head of this device tree. That means we don't have to traverse the entire device tree for the getting booting information. Then second thing on the DTV, we actually the hypervisor create device tree for the control OS and the new, but it takes a lot of time because FTT library uses kind of pattern string matching algorithm, but it's very primitive one. Performance is very poor. So we replace this algorithm with a better one called Royal algorithm, whose time complexity is order of n plus n. Last technique is kind of using multi-core, and we assign the B core for DOM new creation, DOM 0 and DOM new creation. So also we made it possible for concurrent DOM new multiple VM creation. So first one is we just assign CPU4 that is the core to create domain 0 based on gen task list. And the second technique is originally we have to finish the domain 0 routing, and with the Excel command we can create DOM new. However, for the concurrent routing, we move the data structure initialization code inside Excel to hypervisor. Then we assign kind of B4 like CPU4 and CPU5, DOM 0 and DOM new respectively. By doing so, we can concurrently start up two operating system on top of hypervisor. Now let's take a look at the fault recovery mechanism. Basically, we have slightly different fault recovery mechanism for DOM new and DOM 0. While hypervisor is responsible for DOM new failure, hardware reset feature is used for DOM 0 failure. So we reset gen watchdog timer by using gen watchdog demo at DOM new user land. And we also put some hypercode to trigger fault recovery of DOM new inside the panic function in DOM new kernel. For handle the DOM 0 failure, we set the watchdog timer by using watchdog demo and DOM 0. We also put some machine start code inside the panic function in DOM 0 kernel. So in case of Exynos restart. This is the basic architecture, and we implemented this special module here for like Samsung VM Reset Manager. inside the hypervisor. This is for the fast non-new recovery function. Let me explain this more detail. Actually, we can take advantage of conventional VM response function. This is just a combination of destroy domain and create new domain. That means we have to free all the resources from domain and relocate all the resources again by using two hypercodes. However, it takes a lot of time. So in order to reduce this kind of time for the non-new recovery, we implemented new hypercode like VM reset. Within this function, we don't destroy domain entirely. Instead, we just destroy device only, and we just use older data structures for virtual resources by using our new hypercode like phantom reset. Let me explain this more in detail. This figure shows how our non-new recovery works. In case of kernel panic, non-new kernel panic or jam or timeout, the module inside the hypervisor domain shutdown manager take this event and set the reason for VM reset and pause BCP of the new. Then send the virtual IRQ to GenStore, and it goes to the finally Excel, the function leave Excel domain reset. In this function, we close the connection between GenStore and the new. After that, we destroy devices. Then we call our new hypercode like VM reset through the callback function. So we resetting all the virtual resources like this, brand table, VCQ, shared info, PTM table, event channel, or etc. Then we go back to the Excel to invoke this function, and inside this function we reload non-new kernel binary. Then we reload non-new device tree from memory because we preserve non-new device tree in the memory for the fast recovery. And we set a CPU register, then call the hypercode for the unpaused domain. This is the basic sequence of our fast non-new recovery. Now I'm going to talk about I/O virtualization. We have two kinds of I/O virtualization. First one is basically based on power virtualization based I/O virtualization, and the other one is pass-through based I/O device driver support. So we just use open source for virtual network and virtual storage and virtual console, and we added some kind of feature for like touch function to the virtual input device. Then we newly developed kind of virtual camera and virtual audio device driver based on power virtualization model. That means we developed kind of front-end device driver and back-end device drivers. And for the pass-through, in certain cases, some info new, some devices access from exclusively from info new for the performance reason or something. So for to support this kind of use case, we provide kind of pass-through mechanism for the new. However, the thing is that some devices are dependent on other devices, like clock source, regulator, or pin controller. That means if the pass-through devices are spread among multiple domains, then we need to provide a kind of way for multiple domains to access these dependent devices. So our solution is paravirtualize of these three devices for the pass-through supporting the new. So we developed kind of front-end device driver and back-end device driver of those three devices. Now I'm going to talk about our graphics virtualization. This is one of our major contributions for this work. And actually, our architecture is based on graphics API forwarding. That means every graphics API from DOM is forwarded to DOM0. Then DOM0 is processing graphics operation on behalf of DOM by using GPU. That is basic concept of graphics API forwarding. And we have every time application in DOM is started, then the corresponding render thread here, DOM0, is created to handle all the requests from application in DOM. So for example, application in DOM is executed, then the API like EGL APIs and OpenGLES APIs and the data were encoded with our simple protocol by the component like GC and front-end module. Then this encoded data is stored in the shared memory called virtual GPU command buffer. Then we send a virtual event to backend graphics module to ping this data to the backend. Then the corresponding render thread takes this encoded data and decode it to extract graphics APIs and parameters. Then just forward these data to the native graphics library and device driver. This is basic sequence of our graphics virtualization. The key feature of our graphics virtualization is like this. We support the latest graphics APIs like OpenGLES version 3.2. And we have kind of optimization technique for the performance, like shared memory between backend module and front-end module with our simple protocol, and kind of batch transferring mechanism between front-end and backend. Also, we provide adaptive interrupt processing module inside the front-end module, and we also provide efficient graphics buffer management function. Let me explain this, adaptive interrupt processing mechanism. This mechanism is very useful when you have kind of intensive graphics workload inside the guest operating system. So those cases you can choose. Actually, our solution automatically choose interrupt or port based on current request rate and predefined policy. That means our solution calculate the request rate periodically. So, for example, at every 250 milliseconds, we calculate the request rate. The formula is like this: the number of buffer flush operations per designated time. And we have policy like this. For example, we set the threshold like 0.3, which means 75 command buffer flush operation per 250 milliseconds. So based on this threshold, we calculate the request rate and compare. If the calculated rate is over this threshold, then we change the processing mode from interrupt to polling. Otherwise, just keep the interrupt-based mode. With this configuration, we could improve the 5% performance improvement over just interrupt-based processing mode in case of heavy workload inside the operating system. And this is kind of effective graphics command buffer management function. So instead of transferring every single graphics command from front end to back end module, we made a group for the batch transfer. That means we just accumulate every graphics APIs and instruction to the shared memory with this data until we have the special command like GL flush or GL finish or non-void return type APIs. When we have this kind of special APIs, then we just transfer accumulated data altogether to the backend side from front end. Then we flush the buffer. That is a kind of batch transferring mechanism. And the other one is we provide kind of graphics buffer pool inside graphics front end module like this. So we can dynamically expand the graphics memory and shrink the memory based on this mechanism. For example, if the front-end module doesn't have enough graphics buffer, then it asks, virtual GPU module to allocate more memory. Then it adds more memory chunk for like 30 megabyte more memory. Then send the event to backend module to map this kind of increased shared memory. By doing so, we can expand the memory between backend and front-end module. Also, we can shrink the memory when application in the new is terminated and no longer this memory chunk is used. Then we can shrink the memory. Now I'm going to give you some evaluation results. This one is for the hypervisor startup. While original vanilla Gen hypervisor took about 1,479 milliseconds for hypervisor startup, we achieved 69 milliseconds for hypervisor booting by applying our optimization technique. So as you can see, we dramatically reduced booting time of each section of hypervisor booting time. This is comparison between conventional VM restart time and our VM reset time. Conventional VM reset took about 7 seconds. And our VM reset took about 1 second. For Automotive Virtualization, we measured performance of storage device and network device, and we got 95% of non-zero performance and 98% of non-zero performance for sequential read and sequential write for storage throughput. And for the network throughput, we got 93% of non-zero performance. And this one is for showing the functional correctness of our graphics virtualization solution. We tested our graphics virtualization solution by using Khronos CTS. So we ran this Khronos CTS at domain 0 and domain new, and we got the same result like this. We passed all the test cases by using the Khronos CTS from OpenGLES 2.0 to 3.2, which is the latest API, and in addition to the extension APIs. So the total comes 8,383. We passed all the test cases. Now this is the graphics virtualization performance. For measuring this performance, we use the GL Mark II benchmark with the configuration, the Full HD resolution, and off-screen mode. And we got the score like this. For non-zero, we got the score like 661 points for non-zero, and we got the 638 for the view. So that means the relative performance of the new is about 96% of 5 of the zero performance. We achieved this great performance based on our Khronos virtualization solution. Now I'm gonna give you a short demonstration. Actually, we are based on the Khronos platform. We, on top of the Khronos 8090 platform, we developed, optimized the hypervisor, Gen hypervisor. Then on top of this optimized hypervisor, we ran 2 operating systems. These 2 operating systems are Linux-based operating systems. The kernel version is 4.4, and we ran 2 Linux operating systems. The first one is, this cluster operating system, like, having needles, and the second operating system is IDE operating system. We ported generative demo platform here. As you can see, hypervisor booting time takes about 69 milliseconds. And we have 2 operating systems like this on top of our Khronos platform. This is the air conditioning app provided by generative demo platform. And go to the main menu. This is a navigation system also, provided by generative demo platform. This is our virtual camera. So going back to main menu to execute kind of 3D rendering. This is kind of geometric benchmark. So this is the end of my presentation and demonstration. Any questions? Yeah.
I have 2 questions. The first question would be quite easy. So I see that you re-implement your online backup to restart the domain, but have you explored the soft resets like backup?
Soft reset?
Yes, I know that it's not fully implemented on ARM, but I believe that's going to do the same way as what you are doing, meaning resetting the event channel, resetting the P2M, etc. On the ground level.
Actually, we are based on the hardware research for the long-term, hypervisor restart, but we didn't, consider that kind of software research.
Second question, I guess the trickiest one. What's your plan for upstream?
Excuse me?
What's your plan for upstream? Do you plan to contribute to the open source on the user code?
Yeah, that is a good question. Actually, yeah, I'd like, open source these things as soon as possible, but actually, unfortunately, we have not decided yet, open source policy of this work, because some part of the work is based on GPL license, and other part of the work is we developed from the scratch for example graphics virtualization.
So yeah, I totally understand that the GPU virtualization etc. can be totally closed source because sometimes it depends on the hardware stuff.
Right.
But for instance, any modification in Xen on potentially Linux could be upstream and benefit everyone.
Right. So yeah, right. Actually, we will release this, GPL-based code to the public at least before the commercialization. But the time is not decided yet. We need kind of discussion Samsung internally because there are a lot of stakeholders inside of Samsung Electronics. I cannot decide by myself because there are legal group and business division and the kind of open source group, and I'm from research center, so we have to kind of discussion for the kind of open source policy. But obviously we will release this thing before the commercialization, right?
Sorry if you already said this, but I'm asking you again. But so the graphic parameterized driver you wrote, so where do they live? So the front end is in the Linux kernel, and the back end is also in the Linux kernel?
Right, that's correct.
Okay, and that's great. The second question is, are they tied to a specific graphic card, or they are generic OpenGL from the back end?
It's generic OpenGL front end back end, so it could be run on top of Qualcomm processor.
That's amazing, actually. And the way they communicate is via shared memory using RAM cable. Is that the way they communicate?
Yeah. Actually, we provided, RAM table. We provide the kind of pointer of the data, using the RAM table.
Right. Yes. But, okay. So the question is, did you have to make changes to Zen to add the graphic front and back end?
No.
And that's it.
Yeah.
It's a great work. So thank you.
Yeah. Thank you.
So I have a question. So so I only work on upstream. So my question is very generic. Why Zen, but not KVM or JHouse or anything else?
Yeah. Because Zen is great. Actually, for the automotive system, kind of important requirement is kind of the reliability and security. And sometimes we have to run kind of a real-time operating system. Then if you are based on the kind of tied to hypervisor, then we cannot meet the kind of requirement for the real-time latency or kind of strong security. So I think for the automotive systems, Zen is the kind of best solution. Thank you.
Hello, my name is Andreas from Bomb Systems. You just said you achieved real-time characteristics for some domain, yeah?
Real-time?
Real-time characteristics for some domain.
No.
You achieved. No?
Actually, we didn't consider kind of real-time requirement. We just based on the credit to scheduler, and we just run GPOS, two GPOS. on top of a hypervisor.
Okay, I see. And are you planning to go in production with credit scheduler?
Excuse me?
Are you going to go into production with credit scheduler?
Yes, I think so. It is possible because it is the performance is good based on the credit to scheduler. Because real-time requirement is not that critical requirement for the IDI and cluster system. It's not for the ADAS or autonomous driving system, right?
Okay, I see. Thank you.
I actually have one last question. Can I get to it? So I've seen at the beginning that you said that you try to optimize a lot the boots at Zen.
Right.
I totally understand the memory because I don't think that's sufficient what we do today. But I'm a bit surprised that you need to optimize even the device free. So what's your time requirements to boot Zen?
Time.
How fast do you expect them to boot?
It already we achieved 69 milliseconds. The booting time. Zen booting time.
69 milliseconds from 0 to 10 to get the big boot.
Yeah, right.
That's what you want to have, or that's the number you have?
That's what we wanted. Yeah, we achieved our goal. I think I already exceeded my time slot. So
I think we can have one last question. It's like last was finishing the stuff on the sides.
I have a question. Why virtual camera?
excuse me.
Why you have virtual camera? Why not directly adapt the camera to the domain?
It's possible. Just for reference implementation. If you're based on the kind of pass-through camera device driver, then we can provide that kind of solution. It's kind of design choice.
Okay. So also another question about how do you handle GPIO and R2C? GPIO?
GPIO?
Yes, GPIO and R2C.
Actually, for the pass-through device driver support, we parameterize P controller to make the kind of GPIO.
So, sometimes during the board design, you make one register contain 32 GPIO pins, so they may be shared between domain 0 and domain 0. So how to?
Actually, I don't understand what you mean.
Oh, sorry. There is one GPIO controller. It has 32 outputs, 2 pins. So domain 0 is the first half, the 0 to 16, and the domain 0 is from 17 to 31. So how to partition them?
Actually, I don't have exact information about that. Sorry.
All right, we should wrap up because the other room is starting to make sure they're both synchronized. Thank you.